Welcome everyone, and thanks for joining us on this technical talk 7 on the influence of geometry on the dynamic behavior of steel tubular towers for onshore wind turbines. The talk is split into 2 parts. So in the first part, I'll just do an overview on wind turbines, and then I'll hand over to Kaylee for the second part, where she will be looking at the details of the study. Okay, I'm just going to give an overview in this first part of the presentation. So wind turbines, what are wind turbines? Wind turbines are structures that are designed to harness the kinetic energy of wind to produce electricity. As far as the parts of a wind turbine are concerned, the first part is the rotors. The rotors are designed aerodynamically to be able to harness the moving wind speed to cause rotation. The rotation of these rotors is what drives a gearbox. The gearbox drives the generator, and that produces the electricity. So the gearbox and the generator are housed in the part that's known as the nacelle. The assembly of the rotors and the nacelle is supported on top of the tower. This tower is the subject of the study, and the entire structure sits on a foundation. So those are the parts. As far as the growth of wind technology is concerned, we see that if we trace the growth from about the 80s, the rated output has grown from about 50 kilowatts to, at the time that this publication was released in 2008, a rated output of 2.5 megawatts. On the left-hand side, you'll see the rotor diameter that's given in meters. And so you'll see that over the years, the rotor diameter has increased quite significantly. And with that increase in the rotor diameter has been an increase in the rated output of these wind turbines. There was a projection at the time that this publication came out that rotor diameters would continue to increase in diameter, and that there would be an increase in rated output as well. And so that's just shown as a dashed line in this illustration. Next slide. Okay, so why the need for height? Why are these wind turbines getting higher? And what is the impact of that? So to understand that, I've just illustrated here the fundamental wind power equation. So you have this equation, the factors that influence the amount of power that can be harnessed is the density of the air, the area that is swept by the rotor blades, and the velocity of the moving wind. So you see that as the rotor diameter has increased, this has increased the area that is swept by the rotor blades, and that leads to the increase in the rated power output. You also have a situation where, with increase in elevation, the wind speed also increases, and that is also contributing to an increase in the rated output. The equation at the bottom there is just shown to illustrate that as far as the output is concerned, the efficiency of the wind turbine has to be taken into account, and so there is a power coefficient that is added to the equation. Next slide. Okay, so this one just illustrates the increase in wind speed with elevation. Those of you who've done wind loading will be familiar with this illustration. So the wind speed increases with elevation from the surface of the earth until you get to what is known as the gradient wind speed. Beyond the gradient wind speed, you have no appreciable increase in the wind speed. So this just illustrates with an increase in elevation, you also get the benefit of increased wind speed, which also aids in the rated power output. Next slide. Okay, so again, just a chronological summary of the growth in the wind turbine diameter with a subsequent growth in the rated output. So at the time that this publication came out, which was around 2013, the rated output for the turbines at the time was around 3 megawatts with a turbine diameter of 100 meters. So you will notice that as the turbine diameters increase, you also have an increase in the height of the tower. And future projections are that the heights of these towers will continue to grow, and also with an increase in the turbine diameter, as well as an increase in the rated output. So with the increase in height of these towers, there's obviously challenges that arise. And it is these challenges that led to the study that Kaylee is presenting on today. Next slide. So at the time that this study was carried out, which was somewhere around 2016, it was reported that there were some challenges with the circular steel tubular tower that was prevalent, which has pretty much been prevalent, over the years. And some of those challenges had to do with cost, with the increasing height, but also some of the challenges had to do with meeting the dynamic requirements for frequency separation. And so that led to this study that was undertaken to look at changing the geometry. So if we deviate from the circular tapering steel tower to different geometries, would we be able to get geometries that would meet the dynamic requirements for these tower heights? And so that is basically the study that Kaylee undertook. So Kaylee, I will hand over to you for the second part of the presentation. Thank you.
Thanks, Kenny, and thank you for the overview and the introduction. Good afternoon, everyone. So yeah, as Kenny's briefly explained, we'll be going through the contents of a study which the two of us carried out a few years ago. And we subsequently wrote a paper on that study. So this presentation today is essentially just a summary of those findings. So we'll start out with an introduction to the actual topic itself, and then we'll look at the details of the study. And then following on from there, we'll look at some of the basics of wind turbine tower designs, how they're actually designed. And then we'll look at the details of the study and the different analysis that took place. So there were two main components of the analysis, the first being a finite element analysis, and then the second being an analytical approximation method. And then we'll have a look at the results of the study and the findings. And following from there, we'll just go through a brief discussion just to have a look at the various factors that actually influence the tower natural frequency, and then finally concluding. Yeah, so I think all of us sitting here today, it's nothing new to all of us that South Africa has faced significant challenges with regards to electricity supply. I think most of us experienced load shedding today. Kenny and I were actually chatting about it this morning. We were both load shed between 10 and 12. And it seems this afternoon we're all being bumped up to stage 4. So unfortunately, it's something that we've all just become too familiar with. But the government has put in place an integrated resource plan, which they do for a 20-year period over the years. And this plan essentially aims to increase the country's power capacity. And within that plan, a significant portion is actually allocated to renewable energy specifically, all of the different renewable energy components, and wind power forms a part of that component as well. So in the 2010 IRP, what we see is that the total renewable energy allocation was around 17,800 megawatts. And then by 2019, the latest IRP, wind alone was given an allocation of about 17,800 megawatts. So in 2011, the government established a renewable energy independent power producer program. And this program was essentially established to aid the country in moving away from coal power towards renewable energy. And this program has been seen to be highly successful, and it has definitely contributed to a significant growth within the wind power industry. So it's actually resulted in a rapid growth spurt within the industry itself. And for that reason, it's now become recommended that local South African engineers actually start to become more familiar with the design concepts related to wind turbines. And for civil engineers, or for us specifically as structural engineers, that relates to the dynamic requirements of the actual tower, the turbine tower itself. Okay, so then when it comes to the details of the particular study, Kenny did touch on this. The study started out with a desktop investigation, sort of a literature review. And what we found was that steel tubular towers above heights of 80 meters are generally not recommended for wind turbine structures. And this is because of things like limitations on the size of parts that can be transported on our roads. So I think the limitation is around 4.2 meters on the size of a part that can actually be transported. And obviously these towers are getting bigger and bigger, so your parts would essentially be becoming bigger as well. So that does add to some of the challenges. Then the second item is related to the cost. So alternative tower forms, usually concrete, steel, your hybrid towers, those have shown to be more economical. And then the third reason is that it actually becomes difficult to meet your dynamic requirements. Your natural frequencies of the towers start to become a bit more difficult to achieve once they go above 80 meters in height. However, the one thing that we do find is that all of these conclusions are drawn upon basically based on one specific type of tower, and that is your typically uniformly tapering circular steel tower. So other types of towers have not actually been considered, and that exactly was the purpose of the study. So it aimed to assess the viability of alternative types of shapes and geometries and seeing whether or not there were still solutions for towers above 80 meters in height. So the study focused specifically on onshore wind turbines, and we looked at tower heights between 80 meters and 120 meters. And then the towers were assessed for compatibility with a Vestas V112 3 megawatt turbine. And that's purely based on the fact that this is the most common type of turbine for these types of heights. And then the turbine considered also was the upwinded type 3-bladed horizontal axis wind turbine, which is the one we are most familiar with seeing lately. There were also some exclusions from the study. So a cost analysis was not carried out. This is still quite a preliminary study. And then dynamic loading due to wind and seismic effects, that's something else that was also excluded from the study. Okay, then coming to the actual tower of the turbine itself. So we'll just run through a brief overview of how the tower is actually designed. Obviously, wind turbine tower is, that's a really complex structure. And in reality, that would be a multidisciplinary engineering team that would be designing it. So we're focusing specifically on the tower, which is the component that would be designed by structural engineers. And the primary interest of the study would be the carrying out a dynamic analysis on the actual structure. So, okay, so then just to recap, I know we all did dynamic analysis theory, but for many of us, that was a long time ago. So just to recap on that, any structure has a natural frequency, and that natural frequency is essentially a function of the mass of the structure and the stiffness of the structure. And then once that structure goes into operation or is exposed to environmental factors, it would then be subjected to what we refer to as loading frequencies or excitation frequencies. And the fundamental theory is that you want to keep those two frequencies apart from each other, your natural frequency and your loading frequency. If they are too close together or when they coincide, that is when we get the occurrence of resonance or your load amplification, which for us as structural engineers is essentially what we want to avoid altogether. So then coming back to the turbine towers, in our case, we would have two loading excitation frequencies. The first would be your rotor rotational frequency, which will be referred to here as 1P. And then the second would be your blade passing frequency. And because we're considering 3 blades, that would simply be 3P. So there are multiple ways of designing the tower. You could design your tower such that the natural frequency is kept below that 1P value. So if you have a look at the graph there on the right, you would try and keep below the blue line. However, that results in a tower which is classified as soft. So it tends to be a little bit flimsy, and you might not necessarily meet your static requirements for the tower in that case. So the second way you could design your tower is to design it in such a way that its natural frequency would be greater than 3P. So that would be your red line on the graph. You'd want to design it to have a greater natural frequency and to fall in that upper range. That is then a tower which would be classified as stiff. So the tower tends to become a little bit more bulky, you use more material, and it's been shown that that's not the most economical way to design your tower. So ideally, you want to design the tower such that it has a natural frequency between those two loading frequencies. So you'd want it to fall between the blue line and the red line. And that is essentially what we refer to as your safe working frequency or your allowable working frequency. And then here in South Africa, so we don't have any design guides or codes with respect to turbine towers. So we use most studies, and in practice as well, they tend to use this Danish guide, which tells us that you should make use of a 10% safety factor on your excitation frequencies. So that essentially means that you would have a natural frequency on your tower to be within that range. So you would want it to be greater than 1.1P and essentially less than 2.7P. That is your ideal situation. Excuse me. Okay, then looking at the details of the study itself. So as Kenny mentioned, we considered different types of geometries. There were 3 cases that were considered. The first was a linearly tapering octagonal tower, and then the second option was a linearly tapering lower portion, and then it comprised of an upper uniform section. And the third option had a quadratically tapering lower portion with an upper uniform section. And then each of these 3 geometric cases were assessed for 3 different tower cases. So in the study, we referred to those as subcases A, B, and C, and that was for an 80-meter height, 100-meter height, and a 120-meter height. And then when it came to analyzing the tower itself, we considered the tower to have multiple components, and each of those components were 20-meter height subsections so that we could make use of a constant plate thickness for each of those subsections. So obviously for the 80-meter high tower, we would have considered 4 20-meter subsections. Altogether, we actually analyzed 60 different tower cases. because we weren't sure which geometries would be favorable or if we would even achieve acceptable results. So it was purely done on a trial and error basis. And then to start the study, we undertook an initial sizing process just to give us a starting point with the types of geometries and, well, the types of thicknesses that we could consider. And that was based on your static requirements, so looking at your dead loads and then a static wind load as well. And obviously the dimensions and the thicknesses were then played with, and we then tweaked them until they met the dynamic requirements. So for the Vestas V112 3 megawatt wind turbine, this gives us a rotational speed range of between 7.67 and 15.44 revs per minute, which equates to a loading frequency range of between 0.1278 and 0.2573 hertz. So this then gives us an allowable frequency range of between 0.283 and 0.35 hertz. So that is how we designed the tower, such that we would try and get it to have a natural frequency within that range. Okay. So then the first serious analysis portion of the actual study involved a finite element analysis, and this was carried out in Abacus. So the towers were modeled as shell structures, and we used the typical South African steel grade. All of the material properties were input into Abacus, so things like the density, the Young's modulus of the steel, and then Poisson's ratio. And then when it came to the finite element properties, we considered quadrilateral shaped elements, and more specifically four-noded doubly curved shell elements, and then shells with aspect ratios of less than 10. And then we made use of a mesh size of around 0.5 meters. So this mesh size was actually based on a convergence study that we also carried out, where we looked at different types of meshes and different sizes in order to optimize it. So while you might think we're talking about finite elements and 0.5 meters seems rather large, just keep in mind that that is relative to a 100-meter or 120-meter high tower. So yeah, but as I said, that was based on a convergence study, so it was the ideal mesh size to use. And then the tower itself, so we made use of boundary conditions such that we gave it a fixed base. So it was essentially modeled as a cantilever beam. And then we placed a lumped mass at the top of the tower, and that lumped mass accounted for the self-weight of the nacelle, the turbine rotor, and the blades. Okay, and then, so as I mentioned, the tower was modeled on a fixed base as a cantilever beam. And we know that in reality, that tower would actually have been constructed on a concrete raft foundation of sorts, and it would be founded on a particular soil. So we needed a way to take this into account in order to attain more realistic results. And this was done by means of using the spring stiffness method. So the spring stiffness method allowed us to take into account the soil structure interaction. So we made use of typical soil properties from the Eastern Cape area, and this is an area where many other studies have been carried out, and a lot of wind turbines have actually undergone construction in this area. So we used those typical soil properties, and then we also used a typical foundation type. So that then allowed us to calculate the natural frequency of the foundation, taking into account the specific soil properties. So if you have a look at that formula and the little sketch on the right-hand side, once you know your shear modulus, G would be the shear modulus of your soil, and R is the radius of your circular foundation, and Poisson's ratio of the soil, you are able to calculate that K rotational. And you'd obviously easily be able to calculate the mass of your foundation, and then you know the height of your tower, so that allows you to then calculate your natural frequency of the foundation. And then once you've got the foundation and you've got your tower as a fixed beam, you're able to essentially sum those two together by making use of what's known as Dunkerley's method. And that effectively says that the tower and the base are connected in such a way that they behave in series. And so you can essentially sum the square inverse of the two individual natural frequencies to obtain an overall natural frequency. So that's what we did. Okay. And then, so as any good engineer should be doing, we should never just be using software blindly. So we should always be coming up with another method to verify those results. So in this particular case, we made use of an analytical approximation method. And this method essentially made use of the lumped mass principle. So again, what we did was look at the tower as a beam, again, a cantilever beam. And then we broke it up into 10 segments and considered 10 individual masses. So you can have a look at that sketch just to follow along as I explain. And again, we used the mass at the top, which was essentially your 10th segment of the tower. That also took into account those additional loads due to your turbine and your nacelle and your blades. So if you look specifically at the 4th segment of the tower, you would very easily be able to calculate the height at that point. And then you can calculate the mass of that 4th portion as well by using the standard formula to take into account the area, work out the cross-sectional area of the tower at that point. You know the height, and then you know the density of the steel. Once you've got your mass, you're also able to calculate your second moment of area or your moment of inertia. Again, it's just a standard formula based on the geometric properties of the section you're considering. And once you know your I, you can then calculate your stiffness, K, and that also is a standard formula for the stiffness of a cantilever beam, 3EI over h cubed. And then you've got your mass and you've got your stiffness, which are your two major components that you need in order to calculate your natural frequency. So you're essentially able to obtain the natural frequency of that fourth segment of the tower. Then you would repeat that process, obviously calculating it for each of the individual 10 sections of your tower. And once again, you'd use Dunkerley's method to simply add up all those individual frequencies to obtain the overall natural frequency of the tower. So yeah, it seems like a lot of maths, but it's actually all standard basic formula. It's just that it's quite a laborious process. So obviously, if you were doing this by hand, there'd be numerous opportunities for error. So what we did was to just code this method into MATLAB. That way we could simply just put the, input the geometric properties of each of the different towers we are considering, which, yeah, just made life easier for ourselves. We could analyze multiple towers using this method. And then we come to the results. So as I mentioned previously, there were 60 towers that were modeled and analyzed altogether. Purely trial and error, we weren't sure what was going to work and what wouldn't work. And then we obtained adequate results for 25 of the tower cases. So that table there is just a snip of some of the successful cases that we were able to obtain with, yeah, there's some geometry there as well. Okay, and then because we used the two different methods, the finite element analysis in Abacus and then that MATLAB analytical method, what we did was compare the results of the two different methods. And we obtained percentage differences between about 6.25 and 10.53%. So the results were fairly close. Okay, and then there are three main factors which actually influence the natural frequency of the towers. So the first one would be the tower height itself. So in all of the geometric cases that we looked at, there's a trend which we noticed throughout, which was that the mass of the tower increases with increasing height. And this is pretty intuitive and obvious. It is what one would expect. So the challenge is then increasing the stiffness as the mass increases in order to maintain your frequency within your acceptable range. So if you have a look at the two graphs at the bottom there, for case one, what we noticed was as the tower height increased, the base diameter of the tower essentially increased as well. And then again for case one, with increasing tower height, the plate thickness at the bottom of the tower also tends to increase. So this actually makes sense, and it is what you should expect, because essentially your tower is trying to increase stiffness so that it can still produce an acceptable frequency. And this is done by making use of a greater moment of inertia, increasing your plate thickness, and increasing your effective diameter of the tower. And then the second factor which influences the natural frequency of the towers is the cross-section itself. So again, if you look at that graph, what we notice is that the plate thicknesses for case one, now this is when we consider 120 meter high tower throughout. So for all three geometric cases, we're looking at 120 meter high tower. And what we notice is for the first case, which is the octagonal shaped cross-section, we're able to get away with a plate thickness of 60 millimeters at the base. Whereas when we look at cases 2 and 3, which were of circular cross-section, we needed greater plate thicknesses of 70 and 90 moles respectively. So this is actually due to the cross-sectional shape itself. And if we look specifically at the formula for moment of inertia, what you notice is that the I for an octagonal shape is actually greater than that of a circular cross-section. So this increase in your second moment of area is resulting in an approximately 11.4% increase in the stiffness of your actual tower. So you can see by just tweaking your cross-section, it has quite a big impact on your stiffness and effectively the natural frequency. And then the third factor influencing your natural frequency is your longitudinal or your vertical geometry of the tower. So here we looked at only cases 2 and 3 because they were both of circular cross-section. And then if you have a look at the graphs again at the bottom, what you notice is when considering a 100 meter high tower, for case 2, you're able to get away with a 70 mil plate thickness at the bottom, whereas for case 3, we required an 80 mil plate thickness. And coming back to the mass of the tower, both towers being 100 meters in height, case 2 gives you a mass of around 427,000 kilograms, whereas case 3 ends up giving you a mass of about 460,000 kilograms. So essentially, this is because of the fact that case 3, that lower quadratic portion, that tapering portion at the bottom, while it might seem almost aesthetically pleasing, it's actually not doing the tower any favors from a stiffness perspective because you're effectively losing material because of that tapering effect. So yeah, you can see the benefits of the uniform tapering there. Okay, and then again, when we come back to looking at the two results from the two different methods and comparing them, as I mentioned, the percentage differences ranged from about 6% to 10.53%. And then if you have a look at the graph, what you notice is that percentage difference, it tends to increase with increasing tower height. So the 6.5% difference was obtained for the 80 meter high tower, whereas when we look at the 120 meter high tower, we're getting a larger percentage difference of the 10.53%. So yeah, it's actually quite basic, the reason for that. And that is based on the fact that our analytical approximation method made use of 10 lumped masses. So we considered 10 subsections of the tower. And yeah, so essentially for the 80-meter high tower, because we were dividing it into 10 sections, that meant that each of those section heights were 8 meters, whereas for the 120-meter high tower, those 10 sections were 12 meters in height. So now you can start to see the reason of why we're getting that increased percentage difference. It's purely based on your numerical approximation methods and the fact that generally you would consider smaller sections in order to obtain increased accuracy. So it's actually quite self-explanatory. But yeah, nonetheless, I mean, when you're talking about 6% and even 10% difference between two different methods, it still seems to be indicative of rather robust results. So either way, I think it's safe to say the results were definitely verified and acceptable. And then just to conclude, so you can see from the study, the results have shown that, in fact, there are still many other alternatives and there are still options for steel tubular towers for heights of 80 meters and greater. We were able to obtain 25 geometric tower cases for that same height regime, and that corresponded specifically to that Vestas turbine that I mentioned earlier. And it should also be noted that we were able to obtain acceptable frequencies for all of the 3 different geometric cases. So there are numerous different options which can still be looked at. And the study has also clearly shown the influence of the different factors and the geometry and cross-sectional shapes on the natural frequency itself. So what we find is that case 1, the octagonal shaped tower, that tends to be your most favorable because it ends up being more economical, both in terms of structural loading, it's the lightest tower, and in terms of cost and material usage, because you're able to make use of smaller plate thicknesses and smaller diameters. Then case 2 is your second most favorable type of tower. And then lastly, case 3 is considered to be the least favorable type of tower. So by simply deviating from the typically used linearly tapering towers, you're able to see that there are still viable options and different shapes that can be considered. And in fact, that steel tubular towers above heights of 80 meters are in fact still producing acceptable results. Yes, and then that's it from me.